I'm going to present the hardware-software co-design flow integrated in the LLVM, including a simple LLVM VHDL backend. Here's the structure of the talk. First, I'm going to present some points, I hope, which make the understanding of the whole problem description a little bit better. Then I'm going to detail the hardware, and I'm going to give some small results and a conclusion. Okay. The setting of this work, it's part of a larger work, and this part is has been created because I want to test the bus interface, the memory extraction and stuff I'm going to present. And the larger scope of this work is to create a computing environment where I can dynamically switch between hardware and software. But this is only the big picture. I'm going to focus on the stuff pretty much related to the LLVM. So why have I been using the LLVM framework? One big plus is to have a common algorithm description, the LLVM IR. LLVM has a good number of optimizations, which can also probably be used for hardware usage. And LLVM proved to be pretty powerful and easy extensible. So the talk will be structured according to the design flow used using the LLVM and all the parts included. So the first step which is being done is feeding some input algorithm through the LLVM's GCC frontend. After that, the standard optimizations available to the LLVM framework are applied to the input algorithm. And then the next step is the binning pass. The binning pass is a simple pass which decides if the algorithm or the basic blocks looked at are to be executed in software or in hardware. Next step, the LLVM intermediate representation will be stored on disk. This is needed because after that I'm going to create software and hardware out of this common description. And since I have two backends and LLVM doesn't provide an infrastructure to write out the data from one intermediate representation, I choose to store it over there. Okay. Next step is a filter pass. This filter pass uses the information from the binning pass to insert so-called migration instructions, intrinsics. I will talk a little bit more about these migration instructions later on. I'll continue with the software side. The software side uses the, I forgot one thing. The filter pass has a command line argument, and I can tell the filter pass if it should filter for software or for hardware design flow usage. So if I'm on the software part of software side, the filter pass has been instructed to filter out all the hardware, all the blocks which are to be run on the hardware. Okay, after filtering the PowerPC backend is run. The PowerPC backend has been extended to know about the migration intrinsics, and then we have the linking step, and yeah, pretty much standard software design flow. The hardware part itself is generated utilizing the VHDL backend. It's based on the LLVM basic blocks, and the output of the VHDL backend is put into the standard synthesis standard synthesis run of the Xilinx toolchain, which is the synthesis creates hardware description or a netlist out of the VHDL description, and the netlist is then combined with the software part, and then a complete bit stream is created out of both parts.
Can I ask a question?
Probably, I think we have the policy to ask the questions at the end, if you can wait as long.
Yeah.
Okay. One thing which I think is pretty important are the migration points or migration intrinsics. These migrations define implicitly the interface between hardware and software. So they also keep the data flow defined, and they, oops, okay. Yeah, the migration instructions itself are inserted mutually exclusive. So if I'm doing a software side run, for example, the instructions on for the blocks which are to be implemented in the hardware side are replaced by migrate begin and migrate end instructions, which is, oops, this should be migrate end instruction. Yes, and the okay, the whole project is implemented on the Xilinx University program board. It has a medium-sized FPGA, including 2 PowerPCs on board and some memory and some other peripheral stuff. The whole project uses a unified memory architecture, which means that the PowerPC processor and the generator hardware both have access to the same memory space. This is needed if we have some memory accesses out of the hardware part. It needs to have the same view of the memory like the software part. Otherwise, it would make the whole venture pretty complex. The hardware backend itself is pretty similar to the LLVM C backend. So it's not using the DAG selector or something like that. Okay, and now I'm getting more to the details. On the right-hand side, you can see the design flow, and we're currently over here in the binning pass. The binning pass is a simple heuristic, and it decides which basic blocks are software and which are hardware. Currently, the whole design flow works only on basic blocks. However, the binning pass can also work on the function level, but the other, especially the hardware part, is not working on the function level. So I'm going to focus on the basic block level. The binning pass uses different features of the basic blocks to decide if it's more to be implemented in software. Then, for example, it looks for terminator instructions, call instructions, and loops. And data flow features like arithmetic instructions and the absence of phi instructions. And the heuristic is currently pretty simple, but it's just for proof of concept. And I think you can bring every heuristic, you find a corner case for every heuristic, so it doesn't make a difference how sophisticated it is for research at last. The filter pass uses the information from the binning pass. It creates migrate begin and migrate end intrinsics. The migrate begin intrinsic replaces all the code not executed on the current hardware or software side. The migrate begin intrinsic itself is a variable argument function, which means every incoming data dependency is one argument to the migrate begin instruction. Then we have the migrate end intrinsic. Contrary to the migrate begin intrinsic, we can have multiple migrate end intrinsics in one basic block. The reason for that is that this work is based on LLVM 2.2, and LLVM 2.2 doesn't have a multiple return type element. It's only implemented in the trunk or the 2.3 version. So probably in later work it will be adapted to the multiple return types. But right now we have multiple of these. Each migrate end intrinsic represents outgoing data dependencies, and the software backend handles the migrate begin intrinsics completely, which means it enables, or there are pretty minor changes to the software side to integrate the interface between software and hardware. But first, short example. This is a function which has quite a lot of data flow. I'm using this non-inline attribute so that the optimizations of the LLVM are not optimizing away most of this stuff. It's just a small example which fitted on the slides. On the software side, this block is not to be implemented because it's executed on the hardware side. So all the instructions are replaced. As you can see over here, we have migrate begin and migrate end instruction. If here we have enumeration of the migrate begin instruction, which this number tells us at which point in the algorithm we are. We have, for example, multiple points where we're going to hardware, and each point is enumerated. Here's the number of the arguments for the variable argument function, and then we have both arguments, which is the data flowing into the basic block, which are these both arguments for this function. This function is mapped to one basic block, so it's a nice example. Then, after that, the PowerPC assembly is created with these migrate begin and migrate end intrinsics, and these migrate begin and end intrinsics are then transformed or lowered as function calls. And these function calls, here's an example of the migrate begin instruction. Here we have the information at which point we are, so we can set up our hardware in the right way. Then we look for the number of arguments, push the arguments over to the hardware side, and start the hardware backend. So migrate begin is doing a parameter marshalling, pushing it to the hardware and starting it. For the hardware side, there's nothing much to see in LLVM IR because the filter does nothing. It just leaves the LLVM IR alone because this is to be implemented in hardware. But okay, we see a VHDL example for this later on. It's probably then a little bit more interesting. But first, some more details about the VHDL backend. The VHDL backend itself starts off from the same optimized version as the software side, but with the mutually exclusive other blocks filtered out. This basic block, VHDL backend, can only process sequential code. The state machine, which controls which step it's currently processing, is a shift register using a one-hot coding, which makes the decoder pretty simple. The memory accesses break this shift register, so the whole state machine stops, waits for the data to return, and then continues with another shift register. So the shift register is broken up for memory accesses, if there are any in their basic block. For the instructions in the LLVM, the backend uses a one-to-one mapping for each instruction. In the LLVM, there's a hardware element implemented. This uses quite a lot of hardware resources for bigger blocks. Blocks containing migrate intrinsics are not created. This is different to the software part, where the whole stuff is created. Here, we leave away the stuff running in software. The hardware itself is automatically connected to the PLB bus. This is a bus used by the Xilinx tools and enables a unified memory access. Here we see the VHDL output, little cut out with some sections have been cut out to make it fit on the slide. Here we see the shift register. The numbers show that this basic block has 6 steps going from 0 to 5. There are no memory accesses, so we have only one shift register. We have some data registers holding results, and we see over here we have each clock step. We check, for example, if our shift register is currently driven, and then the hardware instructions are executed. Then here in the part cut out, all the other 5 steps are executed, and then here is the last step. Currently not shown is the driving of the shift register and the whole bus interface stuff and so on. Okay, now with these things in place, there's still the problem that the hardware side has to do some memory accesses. The memory accesses, or the bus interface, has been done by a student of mine, Mark Stöttinger. He implemented it. For each, so we have the LLVM VHDL backend over here. There's a multiplexer, and for each memory access, there's a port created within this entity. with this multiplexer element, we connect it to the PLB slave element, which has access to the PLB bus. We choose to implement it as a slave device for debugging, so we can see memory accesses of the hardware backend. If we are running the hardware, we get an interrupt on the PowerPC, so we can check for correctness. Later on, it's planned to make a master device out of this, so we can have autonomous memory accesses by the hardware itself. Then is the most hackish part of this is the extraction of the memory addresses. Software and hardware have to agree on the memory addresses used, and so they have to be transferred from the software side, which has already all the memory addresses included, into the hardware side. So since we're currently running in real mode, we just can extract the memory addresses right off the binary with an M tool, standard binary tool in the Unix environment. We're using the stream editor for merging the extracted the extracted addresses with the hardware backend, and after that, the hardware backend has also the same addresses as the software side. This process is pretty fragile to the reliance on symbol names, and it's currently work in progress because on some larger examples, there's still some corner cases where it breaks, so this is unfortunately not completed. Okay, after that, we are down here in the synthesis phase. We have a complete description of the software. We have a complete description of the hardware. And these both are fed into the Xilinx EDK. That's embedded development kit. The EDK design flow is pretty standard for, there are only a few exceptions. So the Xilinx interrupt handler was much too slow because it was pretty generic and so on. And so we replaced it with a custom assembly interrupt handler to speed up the memory accesses of the hardware part. This is in turn only needed because we have a slave device. And because we have this custom assembly handler, we have to use our own start files and custom linker scripts in the software design flow, working on the assembly output of the LLVM assembly output. And then a bit stream is created, and this is programmed onto the XUP board. Here are some results of the numbers. You can see over here that we have 3 multipliers and 4 adders subtractors. That's the same as the numbers used in the basic block. Otherwise, besides of these, we have pretty lean resource usages. These numbers include the whole bus interface. So besides the one-to-one mapping, I consider them quite good. Here we see some device usage. So for this basic block seen on this example, we use about 1% of the FPGA resources. Yeah. And so I'm getting to the to-do. So I have to, what's still to be done is fix the missing stuff, like the extracting of the memory addresses, and fix some corner cases in more, if I'm feeding it more complicated examples. then to create dedicated optimization passes suitable for hardware implementation. Also, and then what's also on my agenda is to create a more optimized hardware backend, which has not a one-to-one backend, but a more sophisticated backend, which has a more not so demanding resource usage for larger algorithms. Then I'm also looking into fully migratable algorithms. They are partially in the making, and then currently there is no usage of the free CPU power if the control flow is transferred to the hardware. So currently the CPU only waits, and this is of course not so good, but so there should be an operating system or something like that which utilizes the then free CPU power. The goals of this project were an automatic hardware-software co-design flow completely integrated into the LLVM toolchain. This was realized using intrinsics. These intrinsics were made known to the PowerPC backend, and then custom VHDL backend has been created, and this whole stuff has been integrated into LLVM and into the Xilinx tool chain. So given the fact that it's a pretty complicated design flow, it's pretty good integrated. Stuff I did not cover in this talk were some optimization passes which handle, for example, constant arrays for the hardware backend. So, and much more efficient hardware pass, which is using a genetic algorithm for multidimensional optimizations. So, if you have some questions on this stuff, we can probably talk about it or write on. So, thanks for listening. There's some questions?
Yeah, so you create this bytecode for programming the hardware. How long does that actual process take? Is that something that could ever conceivably be done in a JIT, for instance?
Okay, if you think, okay, no, first the question. So the question is, how long does it take to synthesize the hardware, and if it would be possible to JIT it, right? Okay. If you take a simple serial device and an interrupt register or counter or something like that, it takes on about 2 minutes to synthesize. So that's a pretty simple hardware. If you're going to much more complex hardware, like stuff you automatically generate out of software, you are not in minutes, but more than in hours. So thinking about JITting it is probably not the best idea. Okay.
What's the latency of the migrate begin, migrate end? Because if you want to, I assume it's for performance.
Okay, you have the function call, of course, for this migrate begin instruction, and you have a bus transfer for every parameter which has to be function argument which has to be transferred to the hardware. So we have function call, each bus transfer. You can't say absolute numbers because the bus is not.
I just have you found it to be beneficial? Are the workloads for the hardware large enough that the time to describe to the hardware and get the results, to send the commands over there and get the results back?
Unfortunately. Due to the problems I have with the hardware addresses integration, I have not used bigger examples because I had to include the hardware addresses by hand. If you're using a bigger example, it's tedious and error-prone. So I don't have very good numbers for larger algorithms. So currently I don't know.
Is there any long-term future work you're looking at potentially generating programmable hardware? You know, and then actually generating software to run on that programmable hardware?
It would be nice, but
It's a hard problem.
yeah, it's quite hard. So it would be. I think it would be quite some heavy lifting and not enough manpower, I would say, for that.
So it looks like you're compiling in physical addresses into the Xilinx program. So are you using, is that a physical address machine? It's not actually virtually addressed? So that you're always going to be putting that data in the same physical address?
Yes, currently it is like that.
So that whole machine is physically addressed, or what?
Yes, we're currently running in a physical addressed machine.
So like the
So
is just straight through?
yeah, if we're using an operating system, the memory lookup, the lookup of the addresses would be much more complicated, and they would have to be in a way to look up the TLB and stuff like that. But it's complicated as is like that, so probably later on.
You couldn't have a register that you were just writing on the Xilinx where you just gave it an address?
Like an offset kind of.
I extracted the address of the software part, and since we are in real mode, the addresses are one-to-one mapped to the memory addresses, and these are then integrated into the hardware part. So both parts know about, agree on the software addresses.
But if you mean if the hardware was programmed to have a register, can you not write? So you have to just interrupt the chip. You can't actually write, like create a register on the hardware and write to a register on the chip.
Yes, we can. We could. We are not doing it right now for debugging purposes, but we could use a master device in the bus and read and write directly to the memory, any memory location we are thinking of. Is that your question?
No, I'm asking. So the CPU writing to the Xilinx chip, you couldn't create a register on the Xilinx chip that was writable.
Oh, okay. Yes, this would be possible. So you say the hardware, an offset address, and then yeah, that's no problem.
Is there a specific application or set of applications you're targeting with this that you expect to run significantly faster with the hardware assist?
Currently, I was more looking for the Designflow stuff and integrate it into the LLVM. And what I'm looking at, of course, is some computationally intensive workloads without much memory usage. So data streaming application, but nothing special. So I've been working on an example using an AIS encryption, and it creates the AIS algorithm is made to be implemented efficiently in hardware and in software. So I think it's a pretty nice target to test, and it also creates, the LLVM creates some nice large blocks which have some intrinsic parallelism to be exploited. So yeah.
It seems like the sort of thing that people usually target encryption or video compression sort of thing.
Yeah, they are nice targets.
We probably have time for one more question.
Well, so you said you can't do like sequential code, so you can't handle loops on the FPGA?
Yes. So currently we can't handle loops on the FPGA, but we have a hardware backend which can implement whole functions. But to get it running, we first dumped it down only to basic blocks. So if you're using this stuff with these for the basic block with the shift registers, and there's just like in strobe running through the shift register. And if you're doing a loop, you just have to feed the strobe back into this element or to another basic block element. So in this architecture, it's not a problem to implement a loop in the hardware.
Right. So it's like future work, it's just not.
Yes. And you could even use the hardware, for example, to make do it pipelining, because if you put multiple strobes into it, it could do much more computational, but the whole framework isn't into pipelining, so it's just an idea.
Well, you guys can talk about it.
Thanks.